Hi, we just looked at a very simple growth model, and in that growth model we saw that, well, growth stopped, right? Once we got to 144 machines and an output of 120, we no longer got any growth. So we used that very simple model to get at a really important fact that without innovation, if technology stays fixed, growth will stop. Now, sure, the labor supply could get bigger, we could have more workers or something like that, but holding the amount of labor fixed and holding the technology fixed, if we've got a fixed savings rate and a fixed rate of depreciation, there's no more growth at some point. We're going to go up, 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 and then stop. Well, that hasn't been human experience, right? Economic well-being has continued to go way up, right? And GDP continues to go up. And so what's driving that? Well, to get at that, we're going to look at a deeper model, richer model, known as the Solow growth model. Now, what's nice about this model, what I love about this model, is we're just going to add one variable. We're just going to add one more variable to our other model, and that's going to suddenly give us a way to include innovation. Now, just to make this, more interesting maybe or more real, these models are developed by real people, right? And so this particular model is developed by a guy named Bob Solow, and Bob Solow is an economist at MIT. And here's Bob right here. And this is Bob and actually testifying before the House Science and Technology Committee on the need to have multiple models to understand the economy, right? So this is a group of economists here, and we're standing up and we're swearing to tell the truth, the whole truth, and nothing but the truth about why models are important to understand where growth comes from. And in this particular case, to prevent things like the home mortgage crisis, which cost us all a lot of money. All right, so how does Solow's model work? What does Bob's model do? Well, what Bob does is this wonderful thing. He includes one more variable. So everything's the same as before, right? We have labor, capital, depreciation, savings. But we're going to include this thing, A of T, which stands for technology. So when A is low, technology is low. When A is high, technology is high. It's better. So A is just going to be this parameter we can tune to affect sort of how much or how good is the technology in the economy. So if we're making coconut picking machines, right, A is really small, and if we're making incredibly cool, laser pointers and iPhones and stuff like that, right, technology is great. Okay, so this is it. Very simple formula. Output is just equal to the technology at that time times capital to some beta and L to some 1 minus beta. Now wait a minute. This also got a little more complicated. Now I get these betas here. Before I had square roots. Well, if beta equals 1/2, right, so if beta is a half, then this is just the square root of labor times the square root of capital, right? Easy. If beta gets bigger than a half, that means that capital matters a little bit more, and if beta is less than a half, that means capital matters a little bit less. So depending on the technology, it could be that it's a capital-intensive technology, so the beta would be big, or it could be that it doesn't use much capital, and beta tends to be relatively small. So you can estimate different betas for different manufacturing processes or even for different countries, right? And a half was just a convenience we assumed. So that's actually something when you take models today that you'd go in and estimate, you'd figure out what is beta. But for us, since we're just trying to get the ideas here, right, we're going to take beta equals a half. So let's go back just to remind ourselves of where we were before, right? Remember, our total output was 10, because we assumed 100 workers, so 10 times the square root of m. We had a savings rate of 30%, and we had a depreciation rate of 1/4. And we went through and we did all that stuff. We solved for the equilibrium where investment was exactly equal to depreciation. And we got that happened at an output of 120, which required 144 machines, right? So that meant that we were going to invest in 36 new machines, but we'd lose 36 machines to depreciation. So that was our equilibrium. Now we want to say, well, what would innovation do? What innovation would do would be put an A in front of this, right? So now we'd have an A in front of this 10 times the square root of m. So let's do that, and let's see what happens. So now we're going to say that output is 2 times 10 times the square root of m. So what we're going to do is we're going to assume that somebody had a technological innovation, and our coconut machines are now somehow like everything's twice as good. We're twice as productive. Okay, well now let's walk through the math. So what's our investment going to be? Our investment is going to be 0.3 times 20 the square root of m. So that's going to be 6 times the square root of m. And what's our depreciation? Well, that's going to be 1/4 m, right? So that's just m over 4. And so we just have to set these things equal again, right? So 6 square root of m equals m over 4. So that means 24 square root of m equals m. So that means 24 equals square root of m. So that means m equals, right? So our equilibrium is going to be m is equal 496. And output, right, is going to be 2 times 10 times the square root of 496, which is 24, right? So that's 24 times 10, which is 240, which is 480, right? So now our output is 480. Before it was 120, and now it's 480. So if you think about it, productivity doubled, right? Because our technology got twice as good, but long-run GDP went up by 4. Well, why is that? Well, let's look back at our numbers here. Okay, we became twice as productive. So that means that if we'd have kept the number of machines at 144, we now would have an output of 240, right? So we'd have doubled where we're at. But we didn't keep the number of machines at 144. When the technology got better, we actually increased the number of machines to 496. So when you have a technological change, 2 things happen. First, you just get more productive, you get more stuff. Second, because you're getting more stuff, it makes sense to invest in more machines. So there's this multiplier effect. So that means that productivity goes up by 2, right? Output eventually, in the long run equilibrium, goes up by 4, right? And this is what you can think of as sort of an innovation multiplier. Because what's happening, right, is these 2 effects, right? Labor and capital become more productive, so that, boom, you just get more stuff. But second of all, because they're more productive, it makes sense to invest in more machines, so then you get even more stuff. So there's this multiplier. Well, let's think about it. Productivity went up by 2, right? Total output eventually, in the long run, not immediately, because we've got to build all those machines, goes up by 4. Well, that leads to a puzzle, and here's where models are really useful. Is it additive or is it multiplicative? So here's the issue with 2. It could be that productivity went up by 2, and so we get 2 plus 2, and so things went up by 4. Or it could be we get 2 times 2. 2 squared is the reason productivity went up by 4. So we want to figure out, is this additive effect, right? The machine effect plus the productivity effect? Or is it multiplicative? Is it 2 times 2? Well, to make sense of that, what we can do is we can increase the multiplier to 3. Because if it's additive, then we get 6. And if it's multiplicative, we'd get 9, right? So if we make us 3 times as productive, we're going to ask in the long run, do we end up with 6 times as much stuff? Or do we end up with 9 times as much stuff? And again, this is, remember thinking about why do we model? We model to get the logic right. Without the model, it'd be very hard to figure out, is this going to go by 6 or is this going to go by 9? Heck, we might not have even got the second effect of more machines, right? So the model was really useful just in giving us that. Now it's going to tell us the magnitude of the effect. Okay, just to get our bearings again, let's remember where we started from. We start from an existing technology where it's just the square root of labor times the square root of machines. We assume 100 units of labor, so it's 10 times the square root of m. We save 30% and invest that in new machines, right? So that's going to be 3 times the square root of m. We lose a quarter of our machines to depreciation, so that's just m over 4. We set those things equal. We get m equals 144. We get output of 120. That's our equilibrium. Now we want to say, let's triple it. Okay, so let's suddenly assume that there's some a that comes in that's got a value of 3. So now we're going to get 3 times 10 times the square root of m. So our output is 30 times the square root of m. And let's see what happens. Okay, so what's our total investment going to be? Well, that's going to be 0.3 times 30 times the square root of m. So that's going to be 9 times the square root of m. What's our depreciation? Well, that's still just m over 4. So let's set these equal. 9 times the square root of m equals m over 4. So that means 36 square root of m equals m. So that means 36 equals the square root of m. So m is equal to 36 squared, right? So m, we just keep it at 36 squared, right? So m equals 36 squared. What's total output going to be? So if we've got 36 squared machines, which is a big number, what's output going to be? Well, output is 3 times 10 times the square root of 36 squared. So that's 3 times 10 times 36. Well, 3 times 36 is 108, so that's 1,080. So what happened when we made ourselves 3 times as productive? Well, total output went up 9 times. So what we see, remember what was our question? Our question was, is it additive? Are we going to get 3 plus 3 or 6? Or multiplicative, 3 times 3 or 9? The answer is it's going to be multiplicative. We're going to get 3 times 3 is 9. 2 effects multiply on top of one another, right? The first one is we just get more stuff. The second one is we invest in more machines. And those 2 effects get multiplied together. So becoming 3 times more effective means we get 9 times as much output in the long run equilibrium. So let me summarize for a second. In the simple growth model, growth stopped, right? At some point we got to 144 machines and then we no longer had any growth. When we go to the Solow growth model, what happens is if we can continue to increase that A, right, if we can continue to increase our productivity, then growth can continue. But that sort of begs the question, where do increases in A come from? And this has led to what people call endogenous growth models. So in an endogenous growth model, labor can go to things like picking coconuts. Labor can also go to things like investing in new technologies, research and design, and those sorts of things to try and increase that A parameter. So what you could think of is, before all of our labor went to increasing capital, picking coconuts, right? Now that labor could also go to doing research on new coconut picking machines. And what you get in an endogenous growth model is how much labor goes into actually making stuff and how much goes into research and design and thinking, right, is a choice variable in the model, right? And you solve for how much of that you get. Quick summary, right? Growth ceases without innovation. If that's true, everybody should be pro-innovation. And in fact, most people are, right? So here's two quotes. Here's a fun little quiz. One of these quotes is from President Obama, who was a Democrat. The other quote is from President Reagan. I want you to try and guess which quote came from Obama and which quote came from Reagan. All right, so both Reagan and Obama are pro-innovation, right? They are because they're pro-GDP growth, because we want to lift those people out of poverty, right? We want to make everyone better off. Because if we can lift people out of poverty, we make people happier. And what we've learned is the way to do that, right, is first by investing in capital, right, because that makes us, all do better. We get to that 144 machines. But at some point then growth stops, and then you need investment in technology. And investment in technology leads to innovation, which raises the whole thing up. And we get this multiplier effect, right? We get the increased productivity, and then we also get the incentives to produce more machines, right, which raises our standard of living even more. So that's, in essence, what growth theory is. Thanks.